Hey guys, I want to just make a quick video talking about some of the nuances of these notes. A lot of this stuff is a review of chemistry, so I decided not to make a video and just let you guys look at them at your leisure. Okay, first part of this is you got to be able to convert from Celsius to Fahrenheit and back. And this equation right here is the one I use most often when I travel overseas. And I have to convert from Celsius to Fahrenheit, and there's a little example here. And the next slide is going back from Fahrenheit to Celsius. And there you go. You got to know there's the Kelvin temperature scale, which you can get to from Celsius. Absolute zero is theoretical. So there you go. Some of this may be new to you when you talk about, when we look at something called linear thermal expansion. So when metals get hot, they expand. And so a lot of times in this section, there will be problems that will either ask you to find the change in length or find the new length, which are two different things. This doesn't happen on the AP test a lot, but could be there. So the equation, there are actually two of them. For solids, this is the equation that we use. Delta L is, of course, change in length. Alpha is the coefficient of linear expansion, and it is a constant. And different materials have different alphas. Temperatures in Celsius. There's some initial length here, and then you can find the change in length. And the only thing I would tell you to be careful about is that there's a difference between solving for the change in length and solving for a new length. So for this problem right here, there was an initial length of 3. And in the problem, all they gave you is these two temperatures. And they would, either tell you or you'd have to go hunt for the alpha of concrete. So that's what this is. So what they did here is they went ahead and they invoked this formula, and you get the change in length, which is this tiny little bit here. So you had your initial length, you had your change in length, which is this. So if they ask you to solve for the change in length, it would be this tiny little number here. And if they ask you to solve for the new length, well, it would be that. That is the new length, which is the original plus the change. Okay. This problem had other things going on, but I just wanted to mention that. Okay. There are some examples. This right here is a little more complex than we need. We haven't really talked about stress. This is really more of an AP3 thing, but I put it in there, and I probably shouldn't have. Y is called Young's modulus. It's a constant. People kind of freak out when they see this. You get this wacky looking thing from basically taking this equation and putting it in there. But all I want you to know is that it's really usually a lot of plug and chug. Okay. There is a liquid version. This is the volumetric expansion formula, and it's essentially the same thing. Instead of alpha, it's beta. You're solving for a change in volume. A lot of times you'll see this in reference to cars, a car's radiator, something like this. And I'll let you guys look at these problems. Okay. You need to remember that heat is really energy. The symbol is Q. It's measured in joules. There you go. We're going to be talking about something called specific heat, which is something normally I would do. Specific heat is the amount of energy that something needs to absorb before it itself gets hot. And the example I had is you'll see pools, and of course people love being in pools, and that's because pools feel good, because water feels good, right? This sidewalk right next to the pool is probably very hot. People do that, that hot sidewalk dance where they run, and then they jump into the nice cool pool. And the interesting thing is that all of that stuff, the water and the sidewalk, are all being impacted by the sun all at the same time for the same lengths of time. So why is it that the sidewalk is very hot and the pool feels the way that it does? And the reason is because water has a very high specific heat. So it can absorb a lot of energy before it itself gets hot, whereas concrete really can't. Okay. Here's the equation. I call this the MCAT formula because it looks like MCAT. So if you're calculating the amount of heat supplied to something or removed from something, that would be Q. Then you do M times C times delta T. Okay. The units can be different depending on what they're using. Usually it's this, and they're using Celsius for temperature. M is mass, C is the specific heat capacity, which is what we're talking about, specific heat, right? So just think about water and how it feels good to be in a pool because it has a very high specific heat. So it can absorb a whole lot of energy before it gets hot. Okay, and there are some practice problems that you can fiddle with. We would have done this lab in class, okay? And so what's going on here is that they have this chamber and there's water. And they put some unknown sample in there. And so what happens is maybe this unknown sample is very hot. So what happens? When you put it into water, you seal it up. Well, the water warms up, the sample cools off until both are at equilibrium. So this is what happens. So these problems, doing these problems, they're usually going to ask you to solve for something. You know, what is the final temperature of the whole system? What is the specific heat of the sample? What is the mass of the sample? Things like this. And so you'll run into problems that look like this, and this probably looks, you know, kind of scary to some of you guys. So what's going on here is that little sample was very hot. The water wasn't as hot, and neither was the glass and the thermometer and that whole thing. And so what happens here is that the unknown sample starts hot and it cools off. So it's going to lose heat, whereas the water and the chamber are going to gain heat. So the way I usually set these up is I say something like Q lost on one side and Q gained on the other side, right? So in this case, I said that these two things are gaining heat, and this is going to lose heat. So this is the lose side, and this is the gain side. It doesn't matter which side that it goes on. Okay, and then you can solve for whatever you need. The hardest part is keeping track of these delta T's, right? Because sometimes the final temperature is going to be greater than the initial, and other times it's not. It depends on what you're talking about in the problem here. The unknown sample here is going to have a greater initial temperature because it starts very hot and then it's going to cool off. The water is going to have a greater final temperature because it starts kind of cool and it will warm up. So these delta T's can be a little tricky, and you get a whole lot of math. It ends up being more of a math problem. Really, the only physics is figuring out what are the things that are going to gain heat, what are the things that are going to lose heat, and putting them on the right side. And that's really the gist of these problems. The rest of it is kind of an exercise in math. But you might see these problems. So, so I put them in there, I want you to be aware. Last but not least, the phases of matter. I'm always surprised to find out that some of my students really don't know some of this stuff. And you need to know what these are. This picture is important. All right? You're going to heat up ice. Ice starts very cold. You heat it up, so you're adding energy. And that's what this positive slope means. When you get to a flat line, that's when you have what's called a phase change. This flat line means that we have ice and liquid water at the same time, right here. That's at 0. When all the ice is gone, and you only have liquid water, you keep adding energy, Then you get another positive slope where the water warms up. And then you have this gigantic second horizontal line. You know, it takes a while for water to boil if you ever had to make pasta. So that's why this line is always bigger than this little line here. But these two flat lines are your phase changes. During a phase change, there is no temperature change. And so it's a flat line. People wondered for a long time what was going on here. Why are we still adding energy in the form of heat and the thermometer is not rising? And that's because you were trying to break bonds here. So this question is one that you might see. How much energy would it take to go from ice at -30 to, steam at 120? To do that, you're going to use two equations. You're going to use your MCAT equation. And you're also going to use this thing. This sucker is used on the flat lines. And MCAT will be used for these positive slope lines. And of course the problem is going to give you all of these little things. You're going to know what M is and what C is for these various times, right? So what I would have to do to solve this problem is I would have to do MCAT for this small little positive slope line. Then I have to do MCAT for this line. Then I have to do MCAT for this line. And then I'll have to do M times L for this flat line and M times L for this flat line, and then I got to add it all up. So I'd have to add up all of my MCATs and then add up all of my MLs, and that total Q, that total number, would be the total energy it would take to go from ice at -30 to steam at 120. And here again, it's kind of a math problem, and you're sort of accounting at this point for all the little things that are happening. So, I think there's some more practice problems down here. I'm going to find some problems in Wiley that you guys can try and kind of go from there. I hope this helps supplement the notes a bit. Talk to you later.